behind this. It's going to be based off stuff we talked about. We're going to work in an example. We might do two examples, depending on how long the first one takes us, and then give you guys some problems to work to get some practice on this concept. So basically, we were talking about optimization last time. Well, most of the times that we're optimizing, it's with respect to some kind of constraint. We want to maximize profits given a budget, minimize costs given how much we have to pay our employees and how much our costs are. So a lot of optimization is what we call constrained optimization. There's going to be a little bit of vocab here. It's common vocab for this stuff. And then we're going to look at the method of Lagrange multipliers to solve constrained optimization problems. Guys, you've done constrained optimization problems. In fact, some of the problems you'll see in the homework, I think, or maybe even on the worksheet, you could have done in Calc 1. In Calc 1, you probably at some point did optimizing the volume of a box with a square base, given the costs of the sides and the bottom. What we were able to do in those cases was we were able to solve the cost for one of the variables, plug it into the volume function because it was a square base, because so it only had two variables, and make it a single variable calculus problem. So some Lagrange multiplier problems you will see in this section could be done in Calc 1. What we're going to do is look at the Lagrange multiplier method, because that does not require us to get the function we're trying to optimize in a single variable. So this is a little bit more general. So let's suppose we want to minimize the function x squared plus y squared subject to the constraint x plus 2y equals 10. Okay, x squared plus y squared is our paraboloid. We've seen that guy a few times, and then we've got a plane there that's our constraint. The function you're trying to optimize is called your objective function, and the constraint is called the constraint equation. And so what we want to do is look at how these things line up. This is where it gets kind of cool. So I'm gonna do this in Calcplot 3D. I was hoping to already have this set up, but so you're gonna have to give me a minute or whoops. As the door was locked and now it's messed up too. Give me just a sec. All right. Okay, so there's our paraboloid. I'm going to need to adjust this. Give me just a sec. We want to make sure that we can see everything. All right, so there is our paraboloid. Let's see, let's give it a little bit more square. All right, so there's our paraboloid. And then we've got a constraint equation. So we looked at how to do this last time, and we're going to put in some contours as well. And we're going to put in some contours. We're going to add our constraint curve. I'm just going to put, it's a linear function. And so all I'm doing is taking x plus 2y equals 10. That was our constraint equation, and solving it for y, which would be 5 minus x over 2. Okay, so that'll put our constraint equation on there. Now, it's a y equals f of x, so it's not going to put on the plane. It's going to put on what the plane would cut out. And you'll see what I mean here in a second, and then I'll show you. All right. There's our contour plot. So I'm going to zoom in a little bit here. This blue line is our constraint. These are our contours. Now think about what we want to do. We want to minimize the function with respect to our constraint. And so basically what that means is we are on the blue line. So we want to be on the spot on the blue line where the function or the paraboloid is a minimum. Now remember how these contour lines work, right? These are going to start off small as far as z values and get larger as we go out. So we want to be someplace on this blue line where the z value is as small as possible. What we know is the contours get closer to the origin, they get smaller. So we want to be on a contour that's as close to the origin while also being on the blue line, right? So that would put us right in this general area right here. Now, this is where this gets really interesting, is that, okay, well, that's the point we want. So next thing we need to think about is what do our constraint and our objective function have in common at that point? Well, they're both going to have the same normal vector, or at least their normal vector will be pointing in the same direction, right? Because being perpendicular to the blue line at this point will be the same as being perpendicular to the curve. Well, think about what we know. What is a vector that we know is going to be perpendicular to a level curve? And I had mentioned this topic is going to keep coming up again and again. The gradient. So basically, we want the spot where the gradient of our objective function and our constraint are parallel, not necessarily equal. So you want to see what this looks like in 3D. That blue is basically the cutout of the plane. What I could do is, if you want to see it, we could actually add the equation of the plane, x plus 2y equals 10. And you can see that that u is what gets cut out by the plane. So what we're looking for, let's take the plane off, it makes it a little convoluted. The point we're going to be looking for is this point right here, right around a z value of 20. All right. Now that's just doing this graphically. We have not done anything algebraically yet, but what we can see is that we have to be on the blue and we have to also be on the surface of the paraboloid. Well, that's the lowest spot where those two intersect. So we're going to use that idea we just talked about to do this method of Lagrange multipliers, which is this idea of we're going to look for the point where the level curve and the constraint equation have the same normal vector. So let's talk about this. Then we'll generalize to Lagrange multipliers, and then we'll run Lagrange multipliers on this problem. So basically what we're looking at is our constraint equation equals 10 as a single level curve of that g of xy. That g of xy is our constraint. So what we're going to be doing is actually matching up gradients. Again, we only need them parallel. And that's where this guy here, you guys saw it in the videos, called lambda comes in. We don't need the gradients to be equal, we just need them to be parallel. So what we do is we set their gradients to be equal along with this constant multiplier of lambda. And then also we have our constraint equation there, which creates a system of equations. So let's work through the one for our problem. And so we can see how this gets written up. So we have another dead marker. We're the only people who use this room. I don't know how all these markers keep ending up dead. f of x comma y equals x squared plus y squared. And we're subject to the constraint x plus 2y equals 10. And what we do is we call that constraint g of xy. So what we're going to do next, again, nothing bad, nothing hard. We're going to find the gradient of each. So the gradient of f, well, with respect to x, it's just 2x. With respect to y, it's just 2y. The gradient of g, well, 1, 2. Now that won't always happen. You know, that just happened in this particular case. There won't always be constants on one side or the other, so on and so forth. But now what we do is we set the components of here, of the f, equal to lambda times the component of g. Now, as far as solving for your optimization problem goes, in theory, you could put the lambda on either side. But I'm going to show you in a little bit that lambda has a very specific meaning. So we always want to attach lambda to g. Okay. So when we set these equal to each other, we have 2x equals 1 times lambda. Okay, the 2x and the 1. 2y equals 2 times lambda. And then we have our constraint equation. X plus 2y equals 10. All right. Now, here's the key. We have 3 variables, x, y, and lambda. Well, we have 3 equations. 1, 2, 3. So we've created a 3x3 system that provides us an opportunity to get a unique solution. If this was a function of 3 variables, we'd be looking for 4 equations. Well, that would work because the gradients would have 3 components. That'd be 3 of our equations, and then our constraint equation would be the 4th. Now, how you solve these is going to vary from problem to problem, which is why I want to spend some time today doing a couple problems, because how you solve your system, it's going to depend on what your numbers look like. On a system like this, one option is I can get my constraint equation all in terms of lambda and solve for lambda and back solve. Because right here, I know that x equals, divide both sides by 2, so x equals lambda over 2. And here, I could solve for y, but I've got a 2y in the equation. So 2y equals 2 lambda. Excuse me. And then I'm just going to plug those in. So this equation here becomes lambda over 2 plus 2 lambda equals 10. All right. That's 4 halves if we want to do it all in fractions. So 4 halves plus 1 half. That's going to give us 5 halves lambda equals 10. Multiply both sides by the 2/5, right? And we're going to get lambda equals 4. Thank you. Now we can find our x and y. And then we'll see, we'll take a look at the graph to see if that lines up with what we were seeing. So that would mean that x equals 4 over 2, or 2. That would mean, let's see, we didn't quite solve this one out, but if 2y equals 2 lambda, y equals lambda, so y equals 4. And putting that into our original, so f of 2 comma 4 is 2 squared plus 4 squared, 4 plus 16. There's our 20. And again, that happens at the point 2 comma 4. Because depending on what we're asked, we might be asked for the location, the inputs that make the maximum or minimum, or the actual maximum or minimum. So we have a minimum of 20 subject to our constraint that happens at 2, 4. And let's just real quickly take another look at the graph and see that that makes sense. Now we saw that it was at about right here at 20, so that looks good. Then if we look at the location, I know it's really tough to tell on the angle. Let's see if we can get something maybe straight down here. Our picture's got a little bit too much going on it. Let's maybe from the bottom. How about that? A little difficult to tell, but right there, you know, we can see the y is 4. I know it's a little messy here, but there, x is 2. So algebraically, we were confirmed what we were seeing graphically. That is the method of Lagrange multipliers. Again, here's what I want you to take from this. Number one, it is not hard to set up because we have done the gradient, we have done partial derivatives. That's all you're doing is the gradient for each, setting them equal with a lambda. What you're going to find is typically the hardest part on a Lagrange multiplier problem is solving the system, depending on how messy your system is. We had an easy system on this one, so it was easy to do. So some might take more algebra than others. Questions about this first problem? Okay. So like I said, what we're going to do is I'm going to have you guys set a couple up here in a little bit. But before we do, there's 2 more things I want to do. Number one is I want to formalize this idea of the Lagrange multiplier. This is exactly what we just did. This is the method of Lagrange multipliers. It's a 3x3 system if it's a function of 2 variables. It's a 4x4 system if it's a function of 3 variables. That little guy lambda is called the Lagrange multiplier. Remember, we're always putting lambda on the side of our constraint equation. Now, g of xy equals c is bounded and closed. We're guaranteed both a global max and global min. For the problem we just did, x plus 2y equals 10 is a line that goes infinitely in both directions. Okay, so it is not bounded. That's why we only got a minimum. But you would see if we had a, in fact, one of the ones I might have you guys do, if our boundary, if our constraint was a circle, we will have both the max and the min, like the one we looked at on Thursday, if you remember. We brought up the image in Calcplot 3D. We said, oh, look, there's a max and a min on the circle, but we actually took the min at the bottom. Okay. Interpretation of the Lagrange multiplier. I am actually going to use something from the next section to derive this. We'll talk about it more when we get into the chain rule on Thursday, so don't worry about that. We are going to talk about the chain rule. But it makes more sense to talk about the meaning of the Lagrange multiplier now, okay? All right, so suppose x0, y0 is an extremum found by Lagrange multipliers, like the 2, 4 that we just found. Well, what we're going to do is we're going to consider that point as a function of our constraint. Because if we change our constraint, then the place of the optimum value is going to change, right? If we increase our budget, we're going to be able to hire more workers and have them work more hours. If we decrease our costs, it's going to have an effect on our optimal price, our optimal profit. Basically, that's the idea. We're thinking of x0 and y0 as functions of our constraint. That's why we'll need the chain rule, because we're not thinking of them as composite functions as opposed to static points. All right. Now, suppose z0 is the solution. So z0 would be the 20. All right. So right now, answers are 2, 4, and the minimum is 20. But what we're going to do is we're going to pretend like we can move the 2 and 4 around and talk about how the 20 changes in comparison. This is actually kind of cool. So now this z0 is actually a function of c. It's a function of the constraint. That's what makes this a chain rule problem, because it's a composite function. C goes into x0 and y0. Those go into f. Okay, so we got input into the point gets input into F. So the change in Z0 with respect to C, this is the chain rule that we'll talk about next time, is F sub X. So that's our partial with respect to X times dx dc plus F sub Y times dy dc. This is the, again, I skipped ahead a section for this because this is the chain rule. Well, F sub X and F sub Y are equal to lambda G sub X, lambda G sub Y. And this is why we have to stick the lambda on the constraint side. Factor the lambda out. And basically then what you have is the chain rule for the change in G with respect to C. But G is the constraint equation. So basically you end up with a change in constraint with respect to a change in constraint. Now, this is just a, you know, a little bit of hand waving here because we haven't done the chain rule yet. But here, what I want to take is what we started with and what we ended with. This is the most important part. You do not need to derive it. This is what I want you to know. Remember what Z0 was. It was the optimal value. So this is saying the change in optimal value with respect to a change in constraint is equal to lambda. All right. So what lambda is an instantaneous rate of change. All right, let's talk about how we would use that in our context over here. We found that lambda was 4. Okay, and again, this is going to take a second to process, but I'm hopefully going to get a problem for you guys to do today that will help you with this concept. What lambda is a change in the optimal value with respect to a change in the constraint. Okay. Our constraint here was 10. Maybe 10 is our budget, right? And with our budget, we wanted to minimize our costs. So we had a $10,000 budget. We minimized our cost at production at 20,000. Once we had everything else in, 10 was our initial budget. Okay, so now let's talk about the way lambda works. Lambda talks about the way the optimal value is changing with respect to a change in constraint. So what that 4 is we could use that as a way of saying, okay, well, how much is our optimal value going to change if we increase our budget or decrease our budget, right? So let's say I wanted to increase this from 10 to 11. So I increased that to 11. Well, the fact that lambda is 4, that's telling me that my optimal value would go up by about 4. So it works like a derivative. Now it's an instantaneous rate of change. The larger the change we make in our constraint, the less accurate it becomes because it is instantaneous. But what it's talking about is how is our optimal value changing if we were to increase or decrease our constraint. The value of this is we don't have to go resolve the problem. If we're like, okay, we're going to be able to get $1,000 increase in our budget. How much is that going to increase or decrease our profit? We could use something like lambda to get an estimate on that really quickly. Questions about that?
I think once you put into real world terms, it makes a bit more sense.
Okay, good. And you're going to get a chance to do one here in a couple minutes. So that's why we have to attach the lambda to the G side, because that's what allows us to interpret it this way. If we put it on the other side, it's the reciprocal of that, which doesn't mean it doesn't have value, but it's a lot easier to think about the change in optimal value with respect to a change in constraint. Okay, one last thing I want to do, because I'm basically hoping to have everybody do 2 problems today from the worksheet. So let me bring up the worksheet so we can all look at the same thing here. So, I'm going to probably say, the first one I'm going to have you do is either A or B, maybe either one, actually, probably B, just to try a straightforward Lagrange multiplier problem. And you get, for you guys online, if you want to switch it up or in part half do A, half do B, that's fine. They're fairly similar. The other one I'm hoping to get to today is number 5. All right. And what I want to do is I want to actually give a little bit of help on number 5 and setting up the equations for it because of time. I don't want you to be taking time to have to set up the equations, then doing the Lagrange multiplier method. But the reason I want to do number 5 is a problem that I used to give on midterms. So if you can do number 5, you can do anything that any Lagrange multiplier problem I would give you on the midterm coming up. Okay, so if you haven't had a chance to read the problem, we'll read it together. Zoo is designing a giant bird cage consisting of a cylinder of radius r feet, a height 8 feet with a hemisphere on top, no bottom. The material for the hemisphere costs $20 per square foot, and the material for the sides costs $10 per square foot. And we have a budget of $8,000 total to spend. Find the values of R and H to give the birds the greatest space inside, assuming the zoo stays within budget. And there's some reminders of the formulas, but I wanted to set up the equations for you so that you guys can go right into solving, just again, for time's sake. So first off, what are we trying to do? We're trying to give the greatest amount of space. So our objective function is going to be a volume function. And there's going to be 2 pieces to that volume function. There's going to be the upper hemisphere of the bird cage, and then there's going to be the cylinder of the bird cage, right? So basically, our volume function is going to consist of both of those. So the volume of a sphere is 4/3 pi r cubed, but we're only looking at half of it. So 2/3 pi r cubed will take care of our hemisphere. And then for the cylinder, it's plus pi r squared h. All right. So that'll be the volume. That's our objective function. Now our constraint, call it C. Well, that's going to be the cost of this thing. And that is that the surface area of the hemisphere, well, the surface area of a sphere is 4 pi r squared. Again, we only need half of it. So 2 pi r squared, that takes care of the hemisphere, but the cost for that material is $20 per square foot, right? So 20. And we're going to do the same thing for this. The lateral surface area is 2 pi r h for this cylinder. So 2 pi r h, and I believe this was $10 per square foot, right? And we are going to assume that we are going to use every bit of that budget, which is 8,000. So that's our constraint. We'll simplify this a little bit. 40 pi r squared plus 20 pi r h equals 8,000. Now,
Professor, quick question.
Yeah.
I'm following along perfectly, but I do just want to solidify my understanding of C. C is our constraint, and we have 20 times the half of the surface area of a sphere, right?
Yep, half a volume of a sphere and then 10 times half surface area of a sphere.
Okay, so volume of a sphere.
Right. 20 times half surface area of a sphere.
Okay.
10 times the surface area of a cylinder.
All right, perfect, awesome.
And so I'm going to stop there because what we would do next is going to be the method of the Lagrange multipliers. You're going to be looking at the gradient of, we'll call it V, setting it equal to lambda times the gradient of C. All right, and then the rest is going to be partial derivatives and algebra.
And our X and Y values are R and H?
Yep.
Okay,
Yeah, if you want to change those to X's and Y's, you totally can. Just make sure you know which one's which.
yes, okay.
Other questions on this one? Now, again, I'm going to have you start with one of the ones from number 1 first, just to do a straightforward problem, and then this one. But there's a couple of really good questions in this one, specifically B and C, that I want you to practice while you're working with Professor Tar and myself. So we're going to go into groups here in just 1 second. One thing I do want to mention, since I got about as many people here as we're going to, as we talked about, the midterm is going to be on the Tuesday after spring break. Well, has to be done by then. So I'm not going to be able to be here that night. So if there was anybody who was planning on coming in to here to class to take the exam, and you guys I'll talk to afterwards. Be sure to shoot me an email, because there's lots of other options for taking the exam. We'll figure it out. Okay. But for those of you guys who are at home, if you were planning on coming in, shoot myself or Professor Tar an email, and we'll figure out a perfect accommodation for you. Okay. Okay, let's get to work on these problems. And like I said, the second one, I'm really excited for you guys to try that one, to really drive home this meaning of the Lagrange multiplier.